another property of the CES production function is that the isoquants generated by CES production function are negatively sloped and convex to the origin for the positive values of K and L. That is, the isoquants that are generated by this CES production are negatively sloped, and that very isoquants are they are convex to the origin. We have to prove this very property. For this, we need the marginal products of the factor inputs. That is, we will prove it. We will first find the marginal product of the inputs of the CES production function. Let us see our Q, that is production function, is given as our A into alpha K to the power minus beta plus 1 minus alpha L to the power minus beta whole minus 1 divided by beta. So we have to show that this very CS production function is negatively sloped, and it is strictly convex to the origin for the positive values of capital and labor. How will we do this? First, we will first write the marginal products of the inputs. That is, we find the marginal productivity of capital and marginal productivity of labor. First of all, we will find the marginal productivity of labor. That is, we find the marginal products of inputs. That is, we find first the marginal productivity of labor, which is given by the first derivative, the first partial derivative of this production function with respect to labor. So this is equal to dq divided by dl. That means we differentiate this very production function with respect to L. So how it is done? We are sure we have learned in earlier videos how to differentiate a function. So this will become here, this 1 minus beta will become the exponent. We will use the generalized power function rule here. This 1 minus beta will become the coefficient. So this will become 1 minus beta, and we have this alpha A times this alpha and K to the power minus beta plus 1 minus alpha L to the power minus beta whole power minus 1 divided by beta minus 1. We know that when we differentiate, this exponent becomes coefficient and it is subtracted by minus 1. Now here we have to differentiate again with respect to labor, this very function, because we are using the generalized power function rule here. So we have to differentiate this here. This will become this, or I will write this very step here. This is d by dl of this 1 minus alpha L to the power minus beta. So I will show how it is done. So this will become minus 1 divided by beta A alpha K to the power minus beta plus 1 minus alpha L to the power minus beta. This will become here to the whole power. This will become minus 1 plus beta divided by beta, and the differentiation of this will become, this minus beta will become the coefficient again. So this will become here 1 minus alpha L to the power minus beta minus 1. Okay, now how it is done? If we are given, I will show you how we have differentiated. If we are given y is equal to x square plus 3 to the whole power 4. Now its differentiation is here. This will become dy by dx. What we give, we take this 4, this becomes coefficient, and this is x square plus 3, 4 minus 1, and we internally differentiate this very x square. So the differentiation of x square is 2x. This is the generalized power function rule, which I have applied here. If you don't get, no, don't worry, you can check earlier videos. I have shown how we use this generalized power function rule, because we have to, here we have to differentiate with respect to L. Here our L was also present, so we have to internally differentiate this again. So I have written that here. Now this will become, so I will write this stuff. This is 1 divided by beta alpha, A alpha k to the power minus beta plus 1 minus alpha L to the power minus beta. This is minus 1 plus beta divided by beta, and this is minus beta, and it is 1 minus alpha. Here we take the minus 1 is common, so this will become minus 1 plus beta. This is the exponent. Now this beta and this beta will get cancelled. This minus into minus is plus. So we are with this. This is A alpha k to the power minus beta plus 1 minus alpha L to the power minus beta minus 1 plus beta divided by beta, and this sorry, we have here L to the power of this, and we have here 1 minus alpha L to the power minus 1 plus beta. Now what will we do? Let us suppose we write in place of A, I write A 1 plus beta divided by A, because it is also equal to A. In place of A we write this. So in place of A I write this, because this will become also A. So I will write here, this is A 1 plus beta divided by A, and here we have alpha k to the power minus beta plus 1 minus alpha L to the power minus beta to the whole power minus 1 plus beta divided by beta, and we have 1 minus alpha. We can write this L to the power minus 1 plus beta. I can write it as 1 divided by L to the power minus 1 plus beta. Why? We can write, if we are given x to the power minus n, I can write it as 1 divided by x to the power n. It is very simple algebraic rule here. Now what will we do here? I can write this as, this is our A, or I will write this alpha here, 1 minus alpha, that is 1 minus alpha into alpha, A to the power 1 plus beta times alpha k to the power minus beta plus 1 minus alpha L to the power minus beta whole power minus 1 plus beta divided by B, and we have this into 1 divided by L to the power minus 1 plus beta. Now if we can see here, this very thing will become, because if our Q is equal to A to the A into A k to the power minus beta and so on minus 1 divided by 2, so this will become here, this very thing will become here, this red part, this will become, I will write here, this is here 1 minus alpha. In place of this we can write Q to the power 1 plus beta. Since Q is equal to A and this very function, now we are here A 1 plus beta, and here we are also 1 plus beta. So this will become Q 1 plus beta here. And we are with this, what is here? So here actually we have also this A, I will write here. This very A. I forgot here, sorry for the mistakes. It happens when there is so much of the stuff here. So in place of this very, I write what Q to the power 1 plus beta, and we have this L to the power, sorry it is here plus 1 plus beta. Okay. Now for the solving, this will become this will become 1 minus alpha, 1 minus alpha. So first I will write here also A, I forgot here. So this becomes here 1 minus alpha divided by A. Here this is Q 1 plus beta divided by L 1 plus beta. So this will become 1 minus alpha divided by A, and we can write it Q divided by L, Q divided by L to the power 1 plus beta. So this is our marginal productivity of labor, or our MPL is equal to MPL is equal to this. Similarly, our MPK will become, so I will write here, our MPK will become also, so I will write here, our MPK is equal to alpha divided by A, Q divided by L to the power 1 plus, so I will not write it here, this will become messy, I will write it here. Similarly, we can show by that these very steps that our marginal productivity of capital will be equal to, so first I will write here, our MPK is equal to dQ divided by dK, which will be equal to this value, sorry, alpha divided by A into Q divided by L. We would have Q divided by K to the power 1 plus beta. So I will write similarly. We can show this MPK is our this, because of the lack of space I cannot do it here. Now the slope of the isoquant is given by, that is the slope of isoquant is shown by, that is slope of isoquant is equal to slope of isoquant is equal to, that is equal to minus dk divided by dl, which is equal to mpk divided by, sorry, mpl divided by mpk. That is the formula for slope is this, minus dk divided by dl is equal to mpl divided by mpk, or we can write that dk divided by dl is equal to minus mpl divided by mpk. Now our marginal productivity of labor is this, so we will write that very function that is in place of this. We will write this 1 minus alpha, so we have 1 minus alpha divided by A, and we have Q divided by L, Q divided by L to the power 1 plus beta divided by MPK. Our MPK is this, so I will write here alpha divided by A, Q divided by K to the power 1 plus beta. I hope I am making myself clear, because slope of the isoquant is given by that very formula. By slope of the isoquant we mean, actually, if I can show here, if we measure labor on this side, capital on this side, now the slope of this very isoquant, the slope is given by, that is minus dk divided by dl, which is equal to mpk divided by mpl. That is marginal productivity of, sorry, labor and marginal productivity of capital. Now solving this will become, now here this A and A will get cancelled, or I will write it here like this, 1 minus alpha divided by A, reciprocated of this will become A divided by alpha. Similarly, we will write here this Q to the power 1 plus beta, that is Q to the power 1 plus beta divided by L to the power 1 plus beta, and reciprocating the denominator, so this will become this K to the power 1 plus beta divided by L to the power 1 plus beta. Now cancel whatever gets cancelled. Here we can see this A and A will get cancelled. What was it? Sorry, it is here Q. It is Q. Our Q to the power 1 plus beta, Q to the power 1 plus beta also gets cancelled. And here it is minus because this is minus. Now we are with this, that is, let me write this. This is 1 minus alpha divided by alpha k divided by L to the power 1 plus beta. Now this will come out to be less than 0 because of the negative sign. Because it is negative, so this will become negative. Since the value of alpha, actually I forget to write this, the value of alpha lies between 0 and 1, so I will write it here. Alpha lies between 0 and 1. The conditions are also this beta is greater than minus 1. So if this is between minus 0 and 1, k divided by L to the power, this is positive quantity, this will be also positive quantity here. So we will get the value which is less than 0. So we got our dk divided by dl, which is less than 0. When we have the slope less than 0, we say it is a negative slope. We have shown that our the isoquants generated by CES production function are negatively sloped because we got the value dk divided by dl is less than 0. Now we have to prove that the isoquants generated by CES production function are convex to the origin. Now the convexity is shown by taking the second derivative of this dk divided by dl. That is, we differentiate this very function again with respect to L. That is, d square k divided by dl square will become, here this is minus 1 minus alpha, nothing to do with them. Now this 1 plus beta will become the coefficient, 1 plus beta will become coefficient, and we are with k divided by L. And here we have 1 plus beta minus 1, and again differentiating this L by the generalized power function rule, we have to differentiate this L also. Here it is L to the power 1 plus beta. So this is here L to the power 1 plus beta when transposing. So I will write it is here L, actually it is 1 plus beta. Now this will become L to the power minus 1 plus beta. Now differentiating this, I am just saving some space, so I am skipping some steps here. So now differentiating this with respect to L, this will become minus, this will become the coefficient, minus 1 plus beta, L to the power minus 1 plus beta minus 1, this value. So first we have used the generalized power function rule. The exponent becomes here the coefficient, and exponent is subtracted by 1. And we differentiate this L again. Now differentiating this L this L will give us this very value, which I have shown you here. That this will become minus, this is minus 1 plus beta, L to the power minus 1 plus beta minus 1. Now this minus and this minus, since they are all in multiplication order here, now this minus and this minus will become plus. That means we will get d square k divided by dl square is equal to, 1 minus alpha divided by alpha times 1 minus beta k divided by L, 1 plus beta minus 1, and 1 plus beta L to the power minus 1 plus beta minus 1. So this will come out to be greater than 0. this will definitely come out to be greater than 0, because this a alpha is the value of alpha lies between 0 and 1, excluding 0 and 1 itself. B is greater than -1, so when solving this will come definitely greater than 0. That means d square alhamdulillah, dl square, sorry for this, is greater than, actually it is very cold here, I will say it is very chilly, is greater than 0. We have shown first that the isoquants generated by this CES production are negatively sloped by this very relation, because our dk divided by dl is less than 0. And another, we were told to find whether the isoquants are convex to the origin or not. They are shown by this very identity. If the second derivative is greater than 0, we say it is convex to the origin.